So welcome live class number 3. Today is our third lecture on semiconductor science. So today we are going to discuss about the space charge in equilibrium. We actually discussing only about the PN junction in equilibrium. So today's topic is space charge in equilibrium. For this, let's consider so this is the figure. This is the figure which we have found in the depletion region or in the transition region of a semiconductor diode. Here, within the transition region, actually electrons and holes, they are in transit from one side of the junction to the other. Now, some electrons diffuse from the N-type side to the P-type side, and some are swept by the electric field. That is the action for the drift case. Now, to a good approximation, here we consider the space charge within the transition region. This is the space charge. The space charge is shown in here. And as in the previous lecture, we talked about this positive space charge accumulated in the N-type side of the depletion region, as well as the negative charge particle or the negative charge or the negative space charge accumulated in the N-type region, in the P-type region of the depletion layer. Now, due to the uncompensated donor and acceptor ions, we know that these charges arise. Now, this is the donor type charge, that is Nd plus, and as Na minus is the negatively charged particle, so this is the negatively charged region which is actually within the depletion layer. So this entire picture is about only the depletion layer which we found in a PN junction when it is actually at equilibrium. Okay. Now, the amount of charge. What is the amount of charge if the width of the layer is xn0 for the N-type side of the depletion layer? Then the amount of charge resides here is Q equals to, you can represent it as Q plus. So Q plus equals to charge Q, small q, into the capital A, that is the cross-sectional area, into the width, that is xn0, and then the donor, that is Nd. So this is the amount of charge which actually we found in the N-type side of the depletion layer. Now, what is the value of this charge? That is, the charge resides inside the P-type side of the depletion layer. So this will be Q minus, and Q minus will be actually minus of Q, as because the charge here is negative. So minus of Q into capital A x p0, that is the width of the layer, and then the acceptor ions, that is Na. So here actually we have neglected carriers within the space charge region. So the charge density on the n-type side just q times the concentration of donor ions Nd, and the negative charge density on the p-type side is actually minus q times the concentration of acceptors Na. Now the assumption of carrier depletion within W, W means the total depletion width within W, and neutrality outside W is known as the depletion approximation. So what is the depletion approximation? The assumption of carrier depletion within capital W, and then the neutrality which actually holds outside the depletion layer is totally known as the depletion approximation. Okay. Now, so here, as we can see that a dipole is formed about the junction, and since the dipole about the junction must have an equal number of charges on either side, that is q plus, capital Q plus must be equals to capital Q minus. The transition region may extend into the P and N regions unequally depending on the relative doping of the two sides. As you can see that when I have drawn this picture, intentionally I have drawn different width of the depletion layer. That is, in the n-type side, the depletion layer width is not actually equals to the depletion layer width in the p-type side. Now, in earlier days or in your previous classes, when we have drawn this type of pictures, we actually make the depletion layer equal width in both of the junctions, that is, in both sides of the junctions. Now here we make unequal width of the depletion layer, that is, the layer width of the p-type side is not actually equal to the layer in the n-type side. Now why this happens? This happens due to that in this region, that is in this depletion layer or in this space charge region, the approximation or the assumption must hold that the total number of positive charges, that is Q plus, must be equals to the total number of negative charges, that is capital Q minus. Now, as because the doping concentrations are not usually made equal, that is, this is a most generalized concept that we introduce equal number of doping concentrations, that is donor type and acceptor type of ions equal into the p-type or n-type semiconductor. So this is not this may be a particular case, but this is not at all a general case to study. So in a general way, we can consider that these doping concentrations may unequal. Now, if Na and Nd are not equal, but we have to make that capital Q plus equals to the capital Q minus, as because the cross-sectional area capital A is equal, the charge Q is equal, that is small q. So we have to adjust QP0, XP0 or XN0 accordingly, just to make capital Q plus equals to capital Q minus, and that results in a different width of the depletion layer, which actually extends into the p-type side and into the n-type side. Okay. Actually, Oshim, we consider here different values of doping in either side of the p-type and the n-type layer. Okay, so if the doping concentrations are different, but you have to make that capital Q plus equals to the capital Q minus, as because without making the total number of positive charges and the total number of negative charges equal, the depletion region does not form. So whenever the depletion region forms, it actually means that the total number of positive charges in the n-type side must be equal to the total number of negative charges in the p-type side. And to make this number of charges, total number of charges equal, the depletion region width may vary, or rather it varies for this reason. Okay. So, okay, fine. Now, for example, if we consider that the p-type side is lightly doped, than the n-type side. That is, if Na is less than Nd, if Na, that is the acceptor type dopant, is less than the donor type dopant. If Na is less than Nd, so the space charge region must extend further into the p-type material than into the n-type to uncover an equivalent amount of charge. Fine. So for a sample of cross-sectional area capital A, the total uncompensated charge, that is capital Q plus and capital Q minus, on either side of the junction is Q capital A x P0 Na, that must be equals to Q capital A x N0 into Nd. Okay, so this is the case Q plus equals to Q minus. Now let it be equation 1, where xp0 is the penetration of the space charge region into the p material, as well as xn0 is the penetration of the depletion layer into the n-type side. So the total width of the penetration region, what is the total width of the penetration region? It is as simple as we have to sum the values, that is xp0 and xn0. So that will give us the total width of the depletion layer, W. Okay. Now we are going to calculate the electric field distribution within this transition region. We are going to calculate the electric field distribution within this depletion layer or within this transition region. And for this to happen, we consider the Poisson's equation, which relates the gradient of the electric field, which actually relates the gradient of the electric field to the local space charge, which actually relates the gradient of the electric field. Gradient of the electric field means dE dx. Gradient of the electric field, that is dE dx, and it relates to the gradient of the electric field to the local space charge at any point x. And you may consider that this is the equation we actually used it earlier, that is the total charge P minus of N plus the donor charge, that is Nd, and then negative acceptor ion Na. Okay, now let's clear this. So we are going to find the electric field distribution within the transition region, and that's why we started our derivation from dE dx, and that equals to, from Poisson's relation, that equals to Q by epsilon, the total charge, that is P minus of N plus Nd, that is the donut type charge, and then minus of Na. Now, for the region inside the N-type site, that is the region 0 less than x less than xn0, that is the region inside the N-type site, this equation should be dE dx. This equation should be dE dx equals to Q by epsilon into Nd, as because in the region inside the N-type layer, the charge accumulated is actually Nd, that is the donor type ions. And for the p-type side, this will be dE dx equals to minus Q by epsilon into Na, and this is actually the layer minus xp0 less than x less than 0. Okay, so let it be equations 2 and equations 3. Is it clear? These two equations, equation 2 and equation 3. What is small q and capital Q? Small q is the electronic charge and capital Q is the total amount of charge. Solomon. Actually, if you missed our previous two lectures, lecture 1 and lecture 2, then it will be quite difficult for you to continue in this class. So if you have missed our earlier classes, that is lecture 1 and lecture 2, you can find these videos, that is lecture 1 and lecture 2, in this YouTube channel, and you may watch these videos previously before the lecture 3, or if you consider this lecture a bit tough, then please go on, watch the videos, that is lecture 1 and lecture 2. Okay, I think it will be quite easier for you to understand after watching those videos. Now, is it okay? May I continue? Okay. So now from these two equations, that is from equation 2 and equation 3, what we can see, that if we plot these two equations, we can find, let's plot these equations. If this is the x-axis, then if this is the xn0 and this is minus of x p0. Actually, this is the width of the depletion layer and this is the electric field. So in 0 to xn0, that is inside the n-type layer within the transition region, the gradient of electric field is positive. So q epsilon by nd, and within the region inside the p-type side of the depletion layer, d dx is actually negative. So here the value of d dx, here the value of d dx is 1 by epsilon q into nd, what we have found in equation 2, and for this d dx, the value of d dx is equals to minus 1 by epsilon q into na. Now in this, that is the peak, we called it as E0. So from these equations 2 and equation 3, if we plot E versus X, that is electric field versus the distance within the transition region, we found two different slopes. We found two different slopes, positive on the N side and negative on the P-type side. Now there is some maximum value of the field E0 at x equals to 0, and E is everywhere negative within the transition region. Okay? So so we can write integral E0 to 0. That is, actually we are considering this part. Integrating from E0 to 0, that is dE, it must be equals to q by epsilon nd, q by epsilon nd integral dx, and that dx value will be from 0 to xn0, from 0 to xn0, and you can relate it for the region 0 less than x less than xn0. And again for the p-type side, that is from equation 3, if we integrate equation 3 with proper limits, then we can write again integral 0, limit 0 to E0, 0 to E0 dE, that actually minus q by epsilon na integral dx, and that dx value will be minus xp0 to 0. Okay, so these are the two equations, equation number 2 and equation number 3, and we go on integrating these equations 2 and 3 with the proper limits. Now from this integration, or from these two integrations, we can actually found the value of E0, that is the maximum value of the electric field, which is actually within the transition region at x equals to 0. So integrating this, we can find that is minus of E0 is actually q by epsilon into nd xn0, or you can find out E0, that is the value of the maximum electric field, is minus q by epsilon nd into xn0. Or if you go on integrating this equation, you will find E0 that equals to minus q by epsilon Na into minus of x p0, or it will be q by epsilon Na into x p0. No, this will be plus and this will be minus. Okay. So, so here the maximum value of the electric field, is actually, if you calculate from the n-type side, it will be minus q by epsilon nd into xn0, or from the p-type side, if the calculation is done, then you find the value as minus q by epsilon na into x p0, and let it be equation 4. Now, as we are going to find out the electric field, so you can integrate again, or you can find the value of E. Now the value of E, as we know that E equals to minus of dV dx. Okay, so minus of V0 will be integral minus of x p0 to x n0 into capital E into dx. Let it be equation 5. So that is the negative of the contact potential, that is minus of V0. That is the negative of the contact potential is simply the area under the E versus X triangle, which I actually removed here. So that is the area under the triangle E versus X, and from the area of the triangle we actually get the negative of the contact potential, that is minus of V0. Or you can find how, as we know that we can find the area of a triangle, that is by simply calculating half the base into the altitude. So it will be V0 equals to half of half of E0 into W, that is V0, or it can be plus half. Now what is the value of E0? E0 value is minus of q by epsilon nd into x n0, that is inside the n-type side. So after putting the value, you get plus half q into q by epsilon nd into x n0, and then the w. So that is the value of the contact potential V0. Got it? Why can we not write epsilon not in the place of epsilon? স্যার কিছু যদি মনে না করেন একটু মাঝে মাঝে বাংলায় বললে ভালো হয়। Actually, Shubhajit, this is the class of post graduation. Now in everywhere post graduation classes are likely to be taken in English. I am not also quite my conversation is not at all very good in English. I think you can follow my conversation. Okay, I'm not so fast. We are all Bengalis. Fine. So this is the value of contact potential, that is the value of V0 inside the N-type region. And now, what is the value of W? As we know that W is equals to the summation of xp0 and xn0, that is xp0 plus xn0 gives us the value of the total width W, or xp0 is equals to W minus of xn0. Okay, and as we know that xn0 and xn0 into capital ND is equals to xp0 into capital NA. Okay, so here we can find the value of xp0 equals to xn0 into ND by NA. xn0 ND by NA. Now, putting the value of xp0 from this, that is W minus xn0 is ND by NA into xn0. So W will be, taking xn0 common, it will be 1 plus ND by NA. It is xn0 into 1 plus ND by NA, or xn0, the value of xn0, you can find it also with respect to W, that is xn0 will be W by 1 plus ND by NA, W by 1 plus ND by NA, or simplifying this, you will get W into NA divided by NA plus ND. So this is the value of xn0. So therefore, what is V0? Therefore, you can find V0 as half Q by epsilon. Now, putting the value of ND, putting the value of xn0, and then xn0 as WNA by NA plus ND, you will find W square, that is W square NA into ND by NA plus ND. So that is the value of the contact potential V0. Okay, that is the value of xn0, that is the length of the depletion region or transition region inside the N-type site, and that is the value of xp0. It is better to write each topic before discussion. I can't get it pronounced. Okay, so these are the values we already found, that is the value of V0, that is equals to half Q by epsilon NA ND into NA ND by NA plus ND into W square. So from this, W can be found, as W equals to, from this W can be found as twice epsilon V0 by Q into NA plus ND divided by NA ND whole to the power half, or square root of this. Okay, or you can write it as root over of twice epsilon V0 by Q into 1 by Na plus 1 by Nd. As you wish, you can use either of these two equations for W. So in this way, we found the value of the depletion layer width. Is it okay? Jayanto, semiconductor science is all about mathematical calculations, and if you found it boring, you can leave this class. Yes, please. So if you find this class is boring, then from the next day we will drop this class. So you don't want this class of semiconductor science more. Okay, fine. So this will be the last class of semiconductor science. I will report to the coordinator, sir, that these students don't need this class anymore. I don't have previous year questions, as because the previous year previous year examination is also taken online mode. So we have no access to those classes, to those questions. I don't think that this is the way to communicate with the teachers. If you can't follow this class, if you can't have patience for the mathematical discussions, I think you must drop this class. I don't want you in this class anymore. So please leave this class. You are all the students of MSc Physics, and you are bothered about the mathematical calculations in physics. I think it will be better to continue political science or philosophy or history, any art subject. Cannot be done. This is the way to communicate with the teacher. I don't think so. Sorry. So okay. If it is a secondary class, I must report it to the coordinator, sir. But as because all of you are mature students, I don't think it is acceptable. That is, I am going to report about somebody to the coordinator, sir. So if you have any problem with this mathematical calculations or with my class, you may proceed to the coordinator, sir, or henceforth you just discontinue this class. Now we can also calculate the penetration of the transition region into the N and P materials. We can also calculate the penetration, that is, we can also calculate the value of xp0, and xp0 is actually equals to W into Nd. xp0 is actually equals to W into Nd, W into Nd by Na plus Nd, and it will give us W by 1 plus Na by Nd, 1 plus Na by Nd, or that will be equal to, twice epsilon V0 by Q Nd whole divided by Na into Na plus Nd whole to the power half. And xn0, actually you have to remember these values, W into Na by Na plus Nd, and that is equals to twice epsilon V0 by Q into Na by Nd into Na plus Nd whole to the power half. So by these derivations or by these values, we actually conclude the space charge region in the equilibrium, or space charge region rather, at a junction. Now let's move on to PN junction under applied bias. So we already conclude the discussion about PN junction in equilibrium. Now we move on to the PN junction whenever it is biased. That is, now we are moving on to the bias condition. So PN junction is under biased. So whenever we apply any bias, that is, now we assume that an applied voltage or an applied bias of value capital V appears across the transition region of the junction rather than in the N and P neutral regions. Of course, there will be some voltage drop in the neutral material if a current flow through it. But as because in most PN junction devices, the length of each region is small compared with its area, and the doping is usually moderate to heavy. Thus, the resistance is small in each neutral region, and only a small voltage drop appears in the neutral region. So again a physical analysis follows here. That is, now when we are going to apply a voltage, it may be positive, it may be negative, that is immaterial. So whenever we are going to apply a bias or a voltage, if the value of the voltage, let us assume that the value of the voltage is V. Now here, from this particular part of this theory or this lecture, we actually assume that the applied voltage or the applied bias of value capital V, it actually appears across the transition region or across the depletion region. Now why? The entire PN junction, why the voltage applied across the PN junction doesn't appear along or doesn't appear throughout the semiconductor junction or throughout the semiconductor material. Why it appears only in the semiconductor junction? Now, because as you know that after or beyond the depletion layer, the entire region is known as the neutral region. Applying the bias across the PN junction, what we are talking about that this bias is appeared only across the junction. You can find the value, that is the potential drop, only in the junction, as because the length of the semiconductor or the length of the PN junction is actually small as compared to the area, and as because the total depletion region is packed of the space charge regions. That is the reason why we assume that the applied bias it actually appears across the junction. Okay, it is also physically true or it is also practically true that is some voltage drop may appear across the neutral regions, but the maximum value of the potential or the voltage drop which we are applied across outside the circuit, outside the PN junction, it entirely appears along the junction or across the junction. Okay. Now here we shall take positive or V to be positive when the external bias is positive on the p-type side relative to the n-type side. Now the electrostatic potential barrier at the junction is actually lower. The electrostatic potential barrier appeared across the junction is actually lowered when a forward bias, that is VF, as F for forward. So if the voltage is taken to be VF, then the electrostatic potential barrier across the junction is actually lowered. We all know that from the equilibrium contact potential V0 to the smaller value of V0 minus VF. So in our previous class, we actually drawn this potential barrier, that is VP, that is Vn, and this is the value of contact potential V0. Now for forward biasing, that is whenever Vf, that is a positive voltage is appeared or is applied, then this contact potential is lowered by a value V0 minus the applied potential Vf. So it will look like as this, that is here now Vn, this is Vp, and this is the value V0 minus of Vf. So the contact potential or the electrostatic potential barrier is lowered by an amount V0 minus of Vf. And again, for a reverse bias value, if the applied voltage is minus of Vr, as it is reverse bias, so the value should be taken as minus Vr. R stands for reverse. So here in this case, that is whenever we are going to apply a negative potential, negative bias of Vr, minus of Vr, then the electrostatic potential will be V0 minus of Vr, and it will be V0 plus Vr. So it will make the electrostatic potential barrier larger. So for V0, for the n-type, for the reverse bias mode, this contact potential is actually increases, and it will be V0 minus of Vr, and that will be V0 plus Vr. So this is the forward bias case, and this will be the reverse bias case. And as you know, this is the equilibrium case. Okay. So this forward bias case, now we are actually at first consider the forward bias mode, and later on we will move on to the reverse bias mode. Have you any query up to this? Have you any question? Why not Vf minus V0? As because Solomon, okay. Now, as because V0 is the inbuilt potential, V0 is the contact potential which already existing in the inside the junction or in the PN junction. So Vf or Vr, what may be the value of applied bias, that is actually we are applying from the outside of the PN junction. Okay, so V0 is the contact potential which actually exists inside the PN junction, and we are applying either Vf or minus of V0. So the effective potential should be V0 minus of Vf or V0 minus of minus Vr. I think I have already suggested a book for semiconductor science in the group, that is Go On for Streetman Banerjee. Pranav, no, that is not the reason V0 greater than VR. No, potential for a PN junction. Actually, the value is around 0.3 to 0.4, and that value of applied voltage, that is, it is either Vf or it is Vr, we actually make it goes on increasing. That is, without the value greater than 0.3 or 0.4, you can't get current from the PN junction. So how can you establish that V0 is greater than Vr? No, that is the question was that whether V0 is less than Vf or V0 is greater than Vf, why we take V0 minus of Vf. I think, Solomon, I have answered this question. Is it okay, Solomon? Okay, just we can't wait anymore. So let's move on to the topic, that is, so this lowering of the potential barrier occurs because a forward bias, that is P is positive with respect to N, that is, we know that is the case of forward biasing. This raises the electrostatic potential on the p-type side. Whenever we are applying a forward bias, that is, we make the p-type side of the p-n junction positive with respect to the n-type side, actually what happens that it actually raises the electrostatic potential on the p-type side relative to the n-type side, and that results in the decreasing height of the contact potential or the electrostatic potential barrier. Now, what happens for the reverse bias case? For a reverse bias, that is whenever the potential V, that is the applied potential, is equals to minus of VR, the opposite occurs. What is that opposite? That is the electrostatic potential of the P side is now depressed, as because for whenever we are applying a reverse bias, we actually connect the negative terminal of the battery to the p-type side, and which results in depression, which results in lowering of the potential at the p-type side. Electrostatic potential of the p-type side is depressed relative to the n-type side, and that results in an increase in height of the electrostatic potential barrier. So the potential barrier at the junction becomes larger whenever a reverse bias is applied. Okay? Now again, I am afraid that again a mathematical calculation is going to begin. Now I must rub this before. Now the electric field within the transition region can be deduced from the potential barrier. Now at equilibrium dEdx was actually Q by epsilon minus of Na. Therefore, the electric field at the junction, that is Ej, must be equals to minus Q Na by epsilon into xp0. So this is the calculation for the p-type side of the depletion layer, where you can find that the width of the p-type side layer in the transition region was xp0. And in the, if I go on to calculate for the n-type region, the value will be Ej, that equals to minus Q Nd into xn0 by epsilon. So this is for the p-type side and this is for the n-type side. Okay? Therefore, Ej, that is the electric field in the junction, will be minus Qna by epsilon. You can use either of the equations. So putting the value of xp0, it will be W into Nd divided by Na plus Nd, or it will be minus Q Na Nd. Now I am going to put the value of W, epsilon into Na plus Nd, and putting the value of W, that is twice epsilon V0 by Q Na plus Nd whole divided by Na Nd. Okay? So the final value of Ej will be minus root over of twice Q. So after this step, You can write as because NAND is here, NAND is also inside the square root, NAND here and NAND is also inside the square root of the denominator. So you can, as because Q and epsilon is also outside the radical, so move on to the entire inside the radical. You can get twice Q by epsilon, twice Q by epsilon, NA ND by NA plus ND into V0. Now, for forward bias, now when we are going to apply the forward bias, so and in the forward bias case, that V0 should change to V0 minus VF. So in the forward bias mode, that EJ should be changed to, or the value of the V0 should be replaced by V0 minus of VF. As a result, the field decreases. If you put V0 minus VF in case of forward bias in this particular equation, you will find that EJ decreases. And with reverse bias, actually the opposite case appears, that is, you have to put then V0 plus VR and then that EJ increases. So for zero applied bias, what will be the case for zero applied bias? So if you apply the zero applied bias, what will happen? The depletion width is given by W equals to twice epsilon V0, W equals to twice epsilon V0 by Q, Na into Na plus Nd into NAND whole to the power half. That is already we have deduced in earlier today. So that is the case of, that is the value for zero applied bias. So under bias conditions, the same analysis is valid. What we have already discussed, what we have already deduced, all are applicable in also for the biased condition, except that the voltage across the layer should be replaced by either V0 minus Vf or V0 plus Vr. That is only the exceptional thing. So the expression of W, so the depletion region width, what we have already deduced earlier today, that the value of W was twice epsilon V0 by Q into Na plus Nd divided by NAND and whole to the power half. Now, whenever we have applied the positive bias or the forward bias condition, this V0 should be changed to V0 minus of Vf. So for the forward bias case, you need not to worry, or you need not to calculate the entire thing for the forward bias case. Just take the value of the depletion layer width for under no bias condition or at equilibrium, and then you just replace this value of the potential V0 by V0 minus of Vf. So this is the case. This is the width of the depletion layer under forward bias. So we would expect the width W. So the width of the depletion layer should decreases under the forward bias condition. As you can see by comparing these two equations, this is for the case of no bias, or this is the case at equilibrium, and this is the width of the depletion layer when a forward bias is applied. Similarly, if you go on applying a reverse bias, that V0 minus Vf should changes to V0 plus Vr, and that is the reason why the depletion layer width increases whenever a reverse bias is applied. Okay. So actually, in this class, I have discussed about the space charge region, initially the space charge region in the depletion region, and then after completing the PN junction in equilibrium, we move on to apply forward bias, and under forward bias condition we calculate the value of the electrostatic potential barrier, and we have seen that the potential barrier decreases as we apply a forward bias, as because whenever a forward bias, that is whenever the p-type material is made positive to the is connected with the positive terminal of the battery, the p-type layer or the potential of the p-type layer increases, and as a whole the electrostatic potential barrier V0 decreases to V0 minus Vf. And then we move on to calculate the width of the depletion layer, and from the equilibrium case we found that W is actually twice epsilon by Q Na plus Nd into divided by Na Nd whole to the power half into V0 whole to the power half. Now here you can see that all the parameters except V0 is actually constant. You can't change these values of the acceptor ion, you can't change the value of the doping concentration of the donor ion after constructing the PN junction. So only the thing you can change, that is the potential what you apply across the PN junction outside or with the help of a battery. So whenever a forward bias is applied, that value of the electrostatic potential V0, it actually decreases to V0 minus of Vf, and as a result the width of the depletion layer decreases with effect to or with respect to the width of the depletion layer at equilibrium. So I think I've already discussed the Bolina zero biased case. So zero biased case is actually the case what we are talking about in equilibrium. In equilibrium means zero bias case. Now Suleiman, I don't think so, or I just can't comment on this matter. Actually I can't comment on this matter. Actually the study material supplied in VU website is enough. It is up to you. I can't comment you about this matter. I don't think that the entire syllabus is in your study material. I don't think that the entire syllabus is covered. Okay, so let's end this broadcast, let's end this class. And again, frankly speaking, today I am disheartened about this class. Actually, you can't imagine that how much energy is spent for taking this online class. Actually, it is very much tedious to take an online class. Actually, there are two light sources I have used for you to visualize properly. After that, if this is the comment I get from you all or from you, So this is mostly unwanted. Okay. If you found this class effective, or if you find this class interesting, just comment in the WhatsApp group, or I will discontinue this class from tomorrow. Goodbye.